Falcon 9 is in startup.
Right on time. So at this point, the autonomous flight computers have taken over the launch countdown, and stages 1 and 2 will begin pressurizing for launch. Let's listen in to the launch director's final go.
The launch director is go for launch. T-minus 30 seconds. T-minus 15 seconds. E-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engines full power, and liftoff. Go Falcon, go IMAX, go Swifo L1, and go Carruthers.
And we are flying 3 new missions on a million-mile journey to track space weather.
Awesome, there we go.
That is cool. Carruthers separating.
Good afternoon, everyone, and welcome to Behind the Mission Q&A with Principal Investigator Lara Waldrop. My name is Jonathan Makla. I'm the Associate Dean for Undergraduate Programs here in the Granger College of Engineering, and I'm also a Professor of Electrical and Computer Engineering, and have had the pleasure of being a longtime colleague of Professor Waldrop over the past 20 years or so. It's my pleasure to be here today to be able to MC this event. As you just saw, and as many of you witnessed live at 6:32 a.m. this morning, the Carruthers Geocorona Observatory successfully launched into space. And this is a historic first for the University of Illinois, as it is the first Illinois-led NASA mission in history, which is a fantastic feat. I want to thank those of you who joined us early this morning to watch the launch live. I was watching from my back porch with a cup of coffee and YouTube, so it was great to see even if I wasn't able to make it to the instructional facility. If you are not able to make it, you can view the full broadcast and follow mission trajectory updates anytime at our website. To help set the stage for today's conversation, I'd like to take a moment to begin with a mission overview video created by our colleagues at the University of Berkeley, who are collaborators on this project.
Well, my name's Lara Waldrop, and I'm the principal investigator of the Carruthers Geocorona Observatory, which will launch into orbit around the sun and turn around and take pictures of Earth's upper atmosphere.
The exosphere is the uppermost layer of the Earth's atmosphere. It's comprised almost entirely of atomic hydrogen. This is the lightest chemical in existence, and it floats away, essentially evaporates off of the top of the atmosphere into space. The Geocorona, on the other hand, means the light that the exosphere emits. When the sun shines on these atoms, they essentially scatter it off into all directions, and so it glows like a gigantic halo of light in the ultraviolet that surrounds our planet. The first image ever taken of the Earth's exosphere in this geocoronal emission was taken by Dr. George R. Carruthers, the namesake of our mission, and he was a pioneer because he invented the first ever camera that was able to take a picture of ultraviolet emission, ultraviolet photons. Now, the camera that he invented was deployed by Apollo 16 astronauts during their lunar mission in 1972.
The Apollo 16 astronauts didn't bring the camera home with them. The camera that you see behind me, one just like it, is still on the lunar surface today. What they did bring was the film canisters that contained the first pictures of Earth's upper atmosphere, imaged in this ultraviolet glow, that have ever been acquired.
No one had ever been able to measure the outer edge. And in fact, the exosphere extended beyond the outer edge of his picture. It was quite a wide field of view. He got most of it, but he wasn't far enough away, being at the moon, to get the entire field of view. And that was really shocking, that Earth's exosphere can be that big.
The Carruthers Geocorona Observatory, his namesake mission, will be deployed far enough away to image the entire Geocorona in one picture using the same technology that Dr. Carruthers invented. But instead of just taking a few pictures, we will be taking few pictures every hour, day after day, week after week, for years.
We'll be able to create essentially movies, watch a video of how this atmospheric layer responds when a storm hits, watch it change with season over time when the sun is being quiet.
One of the most serendipitous aspects of our mission is that Dr. Carruthers is also a 3-time alum of the University of Illinois, and I'm a professor at the University of Illinois leading this mission. This is Illinois' first NASA mission, so the synergy here is just, it gives me chills, really. It's so remarkable to have carried his legacy into the future in this really special way.
All right. Okay, so we are honored now to be joined by Professor Lara Waldrop, live from Cape Canaveral. And she, as you have seen, is the principal investigator for the Carruthers Geocorona Observatory. She is also the Y.T. Lowe Fellow in Electrical and Computer Engineering here at the University of Illinois in the Department of Electrical and Computer Engineering. Let me just give you a little bit of a background of her and her research, although you can probably guess what a lot of it's about. So modern society's increasing reliance on space-based assets for communication, navigation, and resource management demands a detailed and precise understanding of the time-varying behavior of the terrestrial atmosphere near low Earth orbit. Professor Waldrop's research addresses this need by devising novel sensing techniques to provide empirical estimation of constituent species, temperature, and density, quantities which govern the frictional drag of satellites and space degree, and thus orbital trajectories and collisional hazards. These techniques also support the monitoring and future prediction of transient disturbances caused by space weather, which pose additional dangers to infrastructure through electrical charging of satellite electronics, disruption of radio communication signals from space to ground, and induced currents in the electric power grid. Dr. Waldrop's research enables the unprecedented quantification of atmospheric state parameters both directly via mass spectrometer deployment on small satellites, as well as indirectly through constraint of numerical models of chemical and radiative processes by various dispersed and often intermittent data sources. And now with the data coming from the Carruthers Geocorona Observatory. The intrinsic challenge of obtaining sufficient model constraints for indirect state parameter estimation demands the utilization of a variety of ground and space-based remote sensing techniques. And we're now entering a new era with the launch of this exciting observatory. So, Professor Waldrop, it's great to see you. I assume you can hear us.
Yes, I can hear you loud and clear, and I am thrilled to be here.
Fantastic. We are so glad that you've been able to join us. I know it's a busy day, but first I want to say congratulations to you and your entire team on a successful launch. While we weren't there at the Cape to be able to join you, we had a packed house at the KIF. The monumental steps were packed from top to bottom. It was really fantastic to see so many of our students and staff and community come out to cheer you on. So we have a bunch of questions here for you, and if there's time, we may even go to the audience to add some more from the audience. But to start off with, could you share from your perspective how the launch went and give us some insight into what it was like to be on site during the launch?
You know, it was beyond thrilling. So, you know, it's been a whirlwind of a day. We woke up at 4 a.m, trying to beat the traffic, beat the lines into the Kennedy Space Center, and head out to our viewing platform, essentially. We were on a balcony just a few miles away from the launch site. It's one of the closest launch pads to that particular vantage. And what that means is that when the rocket lifted off, not only could you see it, you could feel it in your bones. It was an incredible experience. It's one of the largest configurations of a Falcon 9. It was a Falcon 9 Heavy in order to get us all the way out where we need to be in deep space in a few months' time. And it was just incredible. So not only the physical experience of watching a rocket lift off, but knowing that the Carruthers Geocorona Observatory was on board and seeing it fly off into space on its way was really incredible.
That's fantastic. Yeah, I've been at a rocket launch before, and you're right. I'm just the feel of all the air rushing by and the noise and just that bone-rattling chill. There's really no other experience like it.
Absolutely. Absolutely. Yeah, it's a little bit like eclipses. Once you've seen one, you become an eclipse hunter.
Yep.
I'm going to be a launch hunter at this point.
Well, hopefully this is just the first of many for you and your team. So I have a series of questions, and I'll work through them. And basically, we've had several submitted by students already, just asking about the mission and your journey to get to this point. So first, to start off with, what are the most significant discoveries or surprises you hope to gain from the Carruthers Geocorona Observatory, and how could they impact our understanding of Earth's atmosphere and space weather?
Well, there's a lot that we don't know about Earth's exosphere. For one thing, as you saw in the movies, it's just so big and so far away that for the past several decades, very few measurements have been made. So we expect to be making a lot of discoveries. We're going to discover just how big it is. We're going to discover just how many hydrogen atoms populate its regions, how they're distributed spatially, and how they change over time. All of these are going to be discoveries. Now, when it comes to space weather, this region is really vital. It plays a crucial role in how Earth recovers from geomagnetic storms. In short, the more hydrogen atoms there are, the faster the recovery. So we expect to be able to use our data that we're getting from this spacecraft to improve our predictions of recovery timescales and better protect those assets in space.
Great, thank you. And I think also, we've both done a lot of experiments in our careers, and there's always the unanticipated discovery, right? I mean, we know we have our mission, we have what we've proposed to do, but there's always the possibility that there's something new that we hadn't thought that we were going to be able to capture with our measurements, that now having this great observatory will allow us to see for the first time.
Absolutely. We will certainly have our eyes open for anything like that. One of the benefits of having our scientific instrument, these ultraviolet cameras, on their own spacecraft platform that we have full control over, unlike any other experiment for NASA's for Earth's exosphere that NASA's ever done. Because we've got control over it, we can point anywhere we want. So if we see something interesting, we just change our science operations plan and start something new and check it out further. So it's very exciting to be so much in control over mission operations the way that we are.
That's a great point. So it's been a long journey, right? I can't remember. Maybe you can fill in the details here. It's been several years since you've proposed and were accepted and worked through the phases to get to this point. So can you tell us a little bit about, during the development of the mission, what sort of has been the most memorable part of that journey from proposal now to launch?
It's all memorable. It's one of those things where it's been such a marathon, and every phase had its own unique flavor. I remember thinking the very beginning when we first got selected, defining the requirements and this is a lot of engineering students are in the audience, and engineering professionals, they understand projects start with defining requirements. What are your requirements? And that's what sets the design. And then after design, you implement it. And after you implement it, you test it and test it again and again in our case. But each one of these phases has been so unique and so intense and involved. It is really hard to name any one aspect of this process, except to say that it's all been
a pleasure. You know, every day that I've been coming to Kennedy over this past week, I've been passing this big movie of President Kennedy saying, we don't do these things because they're easy. We do them because we're hard. And he was talking about going to the moon. And that's exactly how I feel about the Carruthers mission. It was hard. And that's why we did it. But what a tremendous benefit that we're reaping today from all that hard work.
Certainly, and I like, that tie-in to sort of like setting the design requirements and things like that, right? And a lot of our students that are seniors now are going through their capstone design courses, and that's a part of the exercise. And, this is just a real-world example of why that engineering design process is actually used out in the real world.
Absolutely, absolutely. And, I've told the same things to my own students. That's exactly how it works.
Yeah, and so through that process, right, setting those requirements and then actually working with your engineering team that was distributed across many institutions, what was the hardest part of actually designing this piece of high precision machinery that has to be able to survive the heavy Q and be able to survive the launch and actually then operate in an environment where you can't just make a service call if something goes wrong?
Well, so there's numerous small technical aspects of the mission implementation that I could name. But the thing that strikes me the most is really the systems engineering aspect of it. The fact that we had to coordinate so well. Thermal coordinates with power, which coordinates with our payload. So for just a small example, we have to keep our payload in shadow just to keep its temperature stable, because if its temperature starts to drift, now the sensitivity of our instrument to the wavelength that we're targeting, this ultraviolet light, starts to drift. And so now our sensitivity calibration can change. So all of these little details had to work together, and there were dozens of teams that coordinated so well. But the systems engineering aspect of it is really what has impressed me the most with accomplishing something that, as you said, is so unbelievably technically challenging.
So you talked about in your initial remarks about getting to the Kennedy Center today and going through that process. Were you actually in mission control room during the launch? And to what extent are you going to continue to be involved in sort of those mission level control operations?
Well, I wasn't in the mission control room today. I chose to view the launch from the platform so that I could be there with my 10-year-old son. So you mentioned that I've been working on this mission for a few years. In fact, the seed was planted in my mind to start thinking about this instrument and the mission itself when I heard, through the grapevine, so to speak, that NASA they were thinking about sending a rocket out to L1. And I knew this is the perfect vantage for exospheric science. I had to be on that rocket. And when I got that phone call that said, NASA's going to be releasing a solicitation, I remember the phone call. My son was an infant in the carrier on my chest. I was on maternity leave, typing on my stand-up desk, essentially, at home. So he's 10 now. It's been 9.5 years since we first get started. So it was really important to me to be able to watch the launch with him. And like I said, our team works so well. I have full confidence in our project manager to handle things in the mission control room on my behalf during liftoff. After liftoff, when we were essentially in communication through the Deep Space Network ground link for the first few hours in order to establish communication, make sure we can uplink commands to the spacecraft. I was paying a bit closer attention. I sent my son home, essentially, so that I could focus on that. But for that moment of liftoff, I wanted to be with my family.
That's awesome. So you had mentioned L1 and that it's sort of a unique or a rare opportunity to be able to get a ride out there. This launch had several different satellites on it, right? I think I heard it referred to as a cosmic carpool of sorts, trying to get a lot of people out there. So is there going to be any relationship between the Carruthers Observatory and these other missions, or was that just happenstance that you're all on the same rocket launch today?
Well, not exactly happenstance. We certainly didn't coordinate in advance in any concrete way. But this particular vantage, and as you said, launches to this vantage in space, 1 million miles away, they're very rare. And this vantage, though, is so well suited for space weather investigations, both operational, which is what NOAA's SWIFO L1 satellite will be doing, acquiring real-time data that can flow back to Earth and give up-to-the-minute information about the space weather environment that's on its way minutes in advance, as well as the flagship IMAP mission has in situ and remote detectors sitting there upstream of the solar wind away from Earth toward the sun, essentially, as it's flowing past the spacecraft. So again, it's the perfect place to investigate space weather. And so it's not exactly a coincidence that all 3 missions have that as science goals.
Great. So you've launched. There's now a couple months for the satellite to slowly make it, well, not even slowly, fast, make its way to L1. It's 1 million miles away, so it's going to take some time. So how does your role change now as you transition from designing, building, and launch to transitioning to checkout, operations, and eventually scientific discovery?
Well, you said it. It's operations and data analysis and discovery. So our first job is to make sure that we are able to communicate to the spacecraft and tell it what it is that we want it to do. And that's very much Illinois' responsibility of setting the operations plan. So we tell it which stars to point to for calibration. Numerous calibration operations will happen during cruise phase. Things like which of our 6 optical filters do we want to use, or 6 positions in our filter wheel do we want to use for that particular observation? How long do we want to stare? Where are we pointing? Things of that nature. Illinois is planning. These missions operations center at Berkeley, they have a lot of experience running missions. They're running more than one at the moment, in fact. They'll be communicating our commands to the spacecraft and then sending us the data once it comes down. And the moment we get the data, we push it through what we call the science analysis pipeline. This is a gigantic amount of code that was developed also by University of Illinois. And that's where we start making those discoveries and really being able to see the science behind the data.
So looking at the bigger picture, what initially inspired you to focus on the Geocorona, and what do you hope the next generation of scientists will build on from your work?
Well, I really got started as an undergraduate. I joined a professor's research group where he was doing exospheric science from the ground with visible emission. Now, this is a much harder measurement to make. It's much dimmer than the ultraviolet light than the exosphere gives off. But it's also much harder to interpret. And this was the primary way that scientists at that point, during my undergrad years, investigated the exosphere. And so what it meant was that if you went back then to the Wikipedia page on exosphere, it was about a paragraph long. There was a lot to learn. And so once I began my career, I realized this is not just low-hanging fruit in terms of making discoveries, but this exosphere plays such an important role in space weather. This is a major knowledge gap that's affecting our space assets. And so at that point, I tried to get my hands on every piece of exospheric data that had ever been acquired, and I realized we're missing a really big piece by not having wide field images from a distant vantage. That is the ideal way to do it, and that was what I set my mind to doing.
So this mission is named after Dr. George Carruthers, a 3-time Illinois alumnus. How has his work and legacy inspired you?
Well, I tell the story. Before I even knew he was an Illinois alum, his legacy and his impact on exospheric science was so clear that the very first sentence of the proposal that we submitted to NASA mentioned his work. It said, it's been more than 50 years since Dr. George Carruthers took the first picture of the exosphere, and since then, only 3 more have ever been acquired. So right away, his legacy, the fact that he invented the camera that could take photographs with ultraviolet light, has obviously influenced our decision to pursue an instrument with that similar capability. But from what I also understand is that George Carruthers himself was such a, how do I say, scientist educator, which is something that I also personally aspire to be. You know, there's a reason I'm at a university and not at a lab where a lot of NASA missions are managed and led. Doing it from a university where I can get students involved was something that Dr. Carruthers himself valued, and I'm thrilled to be able to carry his legacy forward, especially at the University of Illinois, where he got his start.
And we've had a chance to, and you've had a chance to connect with his family, right? We've met them for a dinner and things like that. So there's still that connection between the university, the mission, and the family, right?
That's absolutely true. They came to the renaming ceremony. So the original name of our mission was GLIDE, Global Lyman Alpha Imager of the Dynamic Exosphere. I came up with that acronym myself. I'm still very proud of it. But when Dr. Nicola Fox at NASA had this idea to rename the mission after him in 2022, we did it right. We had a ceremony at the Beckman Institute, invited his family, and made it a real tribute to Dr. Carruthers' legacy.
That's great. Yeah, I think any good NASA mission has to have a great science, but also a great acronym. So kudos on that. And finally, before we go and see if there are any questions in the audience, and you mentioned this as well, you know, the advantage of being at a university and being able to involve students in the research and being that scientist educator that we all strive to be, and you're a fantastic example of. Many of our students are wondering, you know, how can they get involved either in this project or in future NASA missions?
Well, you know, I think one of the nice things about NASA is that they have such a strong educational component to their federal mission. And so one thing students could consider that's not just relevant to this mission is getting signed up for one of the numerous summer schools that NASA has. So they accept undergraduates, graduate students, even early career postdocs and that kind of thing. NASA has a lot of educational opportunities, internship programs and that kind of thing that will get students hands-on experience with any of the NASA missions essentially that are currently in operation, as well as some of the historical data analysis and also missions in planning. In my case, the students that are working with me essentially found me to some extent. Almost all of them were recruited from the courses that I teach, and I'm really looking forward to teaching another course in the spring and hopefully meeting some new students that can get involved.
All right, now, Laura, if you're okay with it, I think we're going to go to see if we have any questions in the audience here. If you have a question, I'd ask you to raise your hand, and we have some microphones that are going to come around so that Professor Waldrop can hear, so she doesn't have to guess what the questions are. All right, we got one question over here.
Hi, my question is sort of about the future of the mission. So do you have kind of a sense of like what the timeline is for when when arrival at L1 happens, when data starts being collected, like when publications might be expected, when we might start to know what kinds of discoveries are coming from the satellite?
I know the answer to all of those. Yes, yes, and yes. So the first tranche of publications will actually be released soon. We've got a special issue of Space Science Reviews. It was essentially the pre-launch. It's the algorithms. It's an instrument description. It's how we calibrate. It's all of our plans of how we're going to be doing things. And we wanted to get those published before the data becomes public in order to support those kinds of investigations by the public. So that's the first thing. Obviously, we'll have scientific papers coming out that I'll describe in the timeline. So we get to L1, we'll have an orbit insertion in early January. Our nominal 2-year science phase begins March 1st. So that's when we start really staring at Earth and taking picture after picture of Earth nadir. So we've moved out of our primary calibration phase where we're off nadir quite a bit to get some calibration information, the background, for example, and stellar targets, so we can calibrate the intensity, the absolute intensity calibration of the sensor and its sensitivity to ultraviolet light. And so once that starts, data becomes public 6 months later. So September 1st, we'll have it available both on NASA Archive of Record, which is the Space Physics Data Facility, but Illinois will also host its own publicly available data portal. And by then, we expect to have many, many papers at a minimum in draft form, if not submitted and published. So yes, we'll be turning into what I like to call a paper factory once we start to see those images come down.
Cool, thank you.
And that's an important point, right? I mean, this NASA is a public good. This mission is a public good. All that data that you're bringing down, yes, your team is going to work on calibrating it and making sure it's of highest quality, but then it does go out and anyone can make use of it.
It's a requirement of our mission. It's one of the many requirements on our mission.
Yep. All right, I think we have another question over here.
Yeah, hi. I was wondering, what is the rationale for the hour-by-hour images that you're taking of the exosphere? Is that a good temporal resolution to figure out whatever you may want to know about it? Or I guess also what is the time scale of changes in the exosphere generally or after a geomagnetic storm?
That's a great question. Thanks for asking. So we have a 30-minute resolution of the innermost portion of the exosphere. And this is really where the action happens during storms. It's when I say innermost, we think of things in terms of Earth radii, which is roughly 6,300 kilometers in distance. And so that field of view of what we're calling our narrow field imager, the one that has high spatial resolution in this 30-minute high temporal cadence zoomed in, goes out to roughly 7 or so Earth radii around the planet. But then we have an hour-long cadence, hour integrations of a lower spatial resolution, slightly lower spatial resolution image that we expect to capture the entire exosphere so that we can see it out to its dimmest extent. Now, as far as whether or not that captures the variability, we think so. This is a neutral cloud of hydrogen, which means that the only force it's subject to is gravity. And these atoms are essentially in these gigantic, long-lived satellite orbits around the planet. And the only temporal variations that we would expect to happen are either due to that interaction with the ion population around Earth, which to the extent that the ions do change quickly, it has the potential to have relatively quick effects. We think that we would be able to see those. So during a storm, something like 2 hours would be where we have the, let me put it this way. Within 30 minutes, we'll be able to detect 20% variations in density, and that's much faster than any model has shown those magnitude of density changes to occur. So we think we'll be able to capture anything that's happening, both in the inner exosphere and then even in the outer exosphere.
Great, thank you.
Sure.
Sounded like you quoted a mission requirement there.
I did. I slipped right back into it.
I think it's funny. Your inner radius is my outer radius. So, everyone's research domain is a little bit different. But I think one of the great things we have going on here at Illinois in our remote sensing group is that we do now sort of overlap and cover a huge, huge range of the Earth's atmospheric system.
Absolutely. And any single measurement by itself, it really gives an incomplete picture. I mean, they're all important pieces of what is ultimately a very complicated whole. And so having multiple types of sensors, I've advocated for this a long time. Carruthers is a very simple design. We've got one kind of instrument, and we're taking essentially one kind of data, but using the Carruthers data in coordination with other sensors is something I'm very keen to do. And we've already started those conversations with other collaborators doing similar or I should say related, but not the same type of data acquisition. So yeah, we have big plans.
So do you have any other questions from the audience? We got one here, and then we'll go back there.
Okay, so hi. My question is, having created kind of like this amazing new piece of technology that's going to give us so much more information about our planet, is there any possibility that this would be implemented into other planets, like within our solar system, or like some of the moons within just our solar system in general?
That's a great question. I haven't thought of that, but it's certainly possible. I mean, we've studied, this sounds crazy to say, but it's true. NASA has studied the Martian exosphere far more than it studied the Earth's exosphere. With all of these missions to Mars, almost all of them have some sort of Lyman alpha, this hydrogen, ultraviolet hydrogen emission, some sort of a Lyman alpha sensor on board. But none of them have been wide field imagers that sit essentially and stare at the planet and watch it change over time. Almost all of them are either orbiters or they sort of scan spatially. This is the way it had been done at Earth before the Carruthers mission. So I really like your idea. I might steal it down the road because I think that would be really, really beneficial to learn more about these other regions of our solar system that have, very similar types of outer atmospheres as Earth, different reasons that they exist, and they're, serving different roles in those systems compared to what Earth's exosphere is doing, especially with regard to space weather. But it is by far the ideal way to conduct exospheric remote sensing. And so along those lines, I think that would be really useful.
Thank you.
All right, we have another one.
Again, congrats on the successful launch. My question is, so it sounds like there's a lot of collaboration with other universities on this. So I wasn't aware that NASA collaborated with other universities so much for these types of missions. So I was curious, how does that kind of collaboration process work? And I was also curious, it seems like you had a submitted proposal for this. So I was curious, what was kind of the proposal, or what was the process of submitting that proposal, and how does that proposal process kind of work at NASA?
Great, and more great questions. So let me start with the institutional collaborations. So we have essentially 4 primary institutions. They have very well-defined roles. So Illinois, of course, is the lead institution and the principal investigator overseeing the whole mission. Illinois also has the Science, Data, and Operations Center responsibilities. So we define science operations. Once we get on orbit, we set the requirements for the design of the cameras and the design of the rest of the satellite bus to support those cameras. And then we, of course, do the data analysis once we get the data down. So that's really been, it plays to Illinois' strengths. University of California, Berkeley, their strength is multifold. They have run dozens of NASA missions at this point, and a lot of them involve ultraviolet imagers or cameras of some sort. So it was a natural partnership to have the University of California, Berkeley design, build, and even test to some extent our scientific payload. The other expertise they have is in mission management. So our project manager is out of University of California, Berkeley. We joke because he said that the Carruthers mission, we're just a small mission of opportunity in NASA's eyes. We're one of the smallest big missions, so to speak, that they've launched. But compared to flagship missions, which are things that he's managed in the past, he called our project fun. Oh, this will be fun. And so we were really lucky to have him with his role on the team. We also have Boston University. Our deputy principal investigator is based out of Boston University. And then Boston University, in conjunction with actually aerospace engineering students over there, built a secondary science payload. We haven't talked much about it, but it's a little sensor, a photodiode, that will turn around, and essentially it's mounted in a fixed position on top of the payload, and it peeks over the solar panels and measures the solar flux at Lyman alpha. So it's the source of the scattered emission that our primary instrument measures. The way that collaboration has worked is that when we first got when our proposal was being developed, this was in 2018. It was our original proposal, pretty short proposal. We had a, 30-page plan, like most NASA proposals, responding to the solicitation, saying, yeah, we're interested. This is our basic idea. That went in the fall of 2018. By then, we had most of the team members and institutions established. I will say we have a major vendor I haven't mentioned, which is BAE Systems. We hired them, contracted them to build the spacecraft bus based on a heritage design that they've used in other missions. But as far as science partners, it's university system collaborations. So we submitted our proposal in 2018. In late 2019, I got the call from the associate administrator. It was a very early phone call that morning. He woke me up. I'll be honest, it's the first time I've said that in public. I picked up the phone and I said, hello, this is Thomas Zurbuchen. You've been selected to proceed into what's called Phase A concept study. And this is the real proposal. So we had, they gave us 4 months to put that together, or maybe it was a bit longer than that, to put that together. And it ended up being 1,000 pages. It was a monster of a proposal with fold out sheets and budget charts. And it was very involved. That was very intense. And 2 institutions were selected to proceed into that phase. And then there was a really big review process, multi-day review of our concept by a panel of experts. And in the end, NASA chose us to proceed into what they called implementation phase. And at that point, we started purchasing hardware and started the implementation process and the road that we're on today.
Yeah, thank you so much. I mean, 1,000 pages sounds like a lot, so congrats on all the hard work.
Actually, I counted.
All right, and we have another question. Yeah.
Hi, Professor. Thank you for taking my question. I just want to say congratulations again on the launch. I was watching the live stream when it launched, and I remember towards the end of the live stream hearing that we hadn't got a live signal from the satellite yet. I'm guessing that that's come through by now, but I was kind of wondering, you mentioned that at this point you kind of become like a paper factory. You're writing lots of papers about this, but in regards to that live signal, is there anything you're doing with that in the interim while you're waiting for the satellite to reach the L1 point? You like monitoring it to make sure there's like no course corrections that has to be done or things like that?
Absolutely. That monitoring we call ranging. So we have scheduled very routine ground passes with our ground stations, which is the Deep Space Network. This is a network of telescopes around the globe. It's operated by the Jet Propulsion Laboratory. And we have essentially booked time with them very routinely to make sure that we can range, we understand our trajectory above all, and that we can communicate with the spacecraft. And we communicate through their telescopes. So both uplinks and downlinks are through the JPL Deep Space Network system. And we have established communication. In fact, our first pass, which was roughly 2 hours, the 2 hours following separation, which you saw on the broadcast, was very successful. And we accomplished everything we wanted to do during that first pass. And going forward, we'll have a sequence of ranges, and we'll use that information then to plan the exact propulsion maneuver that has to take place roughly a week from now. So once we have a really good sense of what our trajectory looks like, we then build out exactly how we're going to conduct the maneuver, and then it's another series of ranging, essentially, measurements to make sure it worked. And then at that point, we start slowly turning on pieces of the spacecraft, various operations, and instrument commissioning will start happening. And it's all downhill, so to speak, from there.
Thank you so much.
Sure.
Right, we have another question up here.
Hello. Yeah, how significantly do changes in the exosphere affect the other parts of the atmosphere and also in general life down here on the surface?
That's another great question. So I mentioned earlier that the exosphere itself plays this critical role in Earth's recovery from solar storms. So that's a major way that it affects. If it weren't there, then when the storm hits the Earth and energizes the ions that are trapped by our magnetic field, there wouldn't be a very effective way to cool them off. The storms would last a very long time, which means currents would stay strong for a very long time. They would be more likely to couple into power grids on the ground, damage spacecraft electronics, disrupt communication and navigation systems. You get the scintillation, as Professor Makela can tell you a lot about, but you get outages, you lose lock and errors in positioning and things of that sort. So these hazards are very much real, both to our space assets and as NASA's looking forward to putting astronauts on the moon. This would be a very hazardous environment for them. So the exosphere is what helps Earth recover from these storms. The interaction between the exosphere and these ions dissipates that energy. Essentially, it cools off the ions and allows the Earth to recover. So the exosphere is really important, I would say, to life on Earth, even though the changes in the exosphere don't necessarily affect us directly. We're just thrilled that we're going to be able to really pinpoint exactly how that works, because right now our models, our forecasting models, are based on exospheric density estimates that are uncertain by at least a factor of 2. And so what that means is that our storm recovery timescales are uncertain by days. So if you're AT&T and you say, should I turn off my satellite to avoid spacecraft charging? Leaving it off for an extra 3 days is a really big deal. And so having a lot more knowledge about that environment is what we aim to provide.
Okay, thank you so much.
All right, we probably have a time for 1 or 2 more questions if there are any. Got one here up front.
Hi, so I was wondering what has from the original Carruthers telescope that was designed, what design changes or innovations have you made to the new one?
That's another great question. One of the, let's see, what's the best way to explain it? So we have a little bit different kind of detector, obviously. So his detector was a plate that's sensitive. His big contribution was that he invented a way to not just convert ultraviolet photons. I can see that I'm laggy. I apologize.
We can still hear you. We can still hear you.
Okay, good. I'm at the press site over here, and there's a lot of interviews going on. So, but Dr. Carruthers invented a way to image ultraviolet photons, right? And you can't, there's no sensor or even photographic plate that's sensitive to ultraviolet light. And what he developed was a way to convert those ultraviolet photons to visible photons. And not just that, but to keep them essentially where they came from in space is where they landed on the sensor, so that you could actually see the image of their origin, which is what a picture is. Ours is very similar to that, but of course we use a lot of upgraded technology. So our sensor, for example, it's an active pixel CMOS device. It's sensitive to visible photons, not ultraviolet photons. So we still go through the same or similar process of converting those photons. First, the ultraviolet photons hit a photocathode. It's made of potassium bromide. You're all probably familiar with Einstein's photoelectric effect. When you shine a high enough energy photon on a particular metal, it will release an energetic electron. That's exactly what happens. We call it a photoelectron. Comes out the other end. We amplify that through a microchannel plate that keeps all of those electrons essentially in the little channel so that we can maintain their position information. And then those electrons impinge on a phosphor screen that releases a green photon from every electron that hits it, at least to a quantum efficiency. And then it's those green photons that we image. So the detection process is a little bit different. We're not using photographic plates, but to the extent that we're still imaging ultraviolet photons, there's a lot of overlap between his design and ours.
All right, thanks.
Sure.
All right. Well, Dr. Lara Waldrop, you alluded that there's a lot of things going on and lots of press interviews going on. I really appreciate you taking the time out of your busy and exciting day to give us this incredible insight into the mission, how you got to where you are, and where you're looking to go with this exciting observatory. Congratulations again to your team on a successful launch, and we hope you get some well-deserved rest in the next few days. The Carruthers Geocorona Observatory represents not only a milestone for our campus, but also a step forward for space science and exploration. We look forward to following the mission and celebrating its continued success. Thank you to everyone that has joined us in person and virtually for today's event. We hope you have a great rest of your afternoon. Thank you.
Thanks, everybody. It was I really, really appreciate your interest. Go Carruthers.
Go Carruthers. See, now you have a future. That's all you got to do. Design the next mission that will image the corona around Mars. Yeah. Good.
I was like, I recognize him, and then you say to me, I'm like, who knows?
Things been going well.